Okay, so what we've been doing and what we've been talking about is sound. And I guess it was Friday, we talked about our waves, that I can have a transverse wave, and my transverse wave will go like this. It'll go up and down. I can have a longitudinal wave, and that's the one that I'm going to get what we call rarefication and compression. And you might think of this as a pulse through a slinky. Because that's one of the things that we can look at. We also talked about that if I had a string and I sent a pulse and I had a fixed in, that the speed was related to our idea, and it actually works out to be like this. It's related to the elastic property divided by the inertial property. So if I were with a string, so if we did this with a string, the speed of the wave was going to equal the square root of the tension divided by mu, which was our linear density. Okay. And that makes sense because the tension in the string is going to guide how I'm doing things. So I want to be able to keep those pieces out. So I've got that tension in the string. But if I'm thinking about air or water or something that's more three-dimensional, the same speed is going to be the same thing, except now we're going to deal with the bulk modulus divided by the density. It's still the inertial property that we're looking at, but it's the bulk modulus that we're dealing with. And that's for when we're dealing with 3D type things. We also said the speed is going to be related to the wavelength times the frequency, or it's the wavelength divided by T. And this time, where that T is tension, this T is period. So that we're looking at how that wave progresses. Now, one of the interesting things, and if you went outside this week or you were out dealing with the various air, we do know that the speed of sound or in water or something else, because remember, these are all mechanical waves. Those are all mechanical waves, that it is temperature dependent. So we take the speed of sound as 331 meters per second at 0 degrees C. And that's our baseline speed of sound. And you probably experienced that as you were dealing with going out in the cold and things like that. But we can actually use it as my 331 meters per second. And this is temperature in Kelvin divided by 273 degrees Kelvin. Now, this is only one equation for my temperature of sound. You may see when we're going to actually measure the speed of sound later on as one of our laboratories. So as one of our laboratories, we're going to do the 1 over r squared. We're going to do measuring the speed of sound. We're actually going to measure the speed of light as well in the laboratory. But you may see different forms of this equation to get the temperature dependence. So if I look at outside right now, okay, and we say that we're saying that the temperature is at freezing is 331 degrees Kelvin. And now we're going to look at our temperature as what's in the classroom as 273 degrees plus 72 degrees, because that's going to convert to Kelvin. And I'm going to divide that by 273 degrees. We're going to get 331 degrees Kelvin. And if I do that arithmetic, and since it's morning and I haven't had my coffee yet and I haven't had any caffeine, this is going to be 345 divided by 273. That's going to equal 372. Oh, this isn't Kelvin. This is meters per second. Guys, let me get away with stuff. That's meters per second. I get 372 meters per second. Let me do that again, just to make sure I didn't screw anything up. Yeah, and I got 372. Oops, I did screw something up. You guys, let me get away with something. This is Kelvin. This is Fahrenheit. And 72 degrees, this is not the conversion to Kelvin because this was in Fahrenheit. This should be more like 26 degrees Celsius. This was the conversion with Celsius. Now, why did you know that I knew that that was a wrong answer? Because that speed looked a lot faster than what it should be. So we're going to try this again. 273 plus 26 divided by 273. Second square root. Oops. Okay, try this again. This is 273 plus 26 is 299. That looks better. This is 346 meters per second. Yeah, we would all be roasting if it were 72 degrees Celsius. It's not a good thing. So don't let me get away with stuff. Okay. Don't let me get away with stuff, because that's one of the hazards of making up problems out of my head, is that sometimes I forget certain things. Okay. Now, a couple of things we want to look at. So we talked about the speed was related to the square root of B, which we said is the bulk modulus. And that actually is a really interesting thing. And I'm going to go ahead and write out our density. But my bulk modulus, if you remember at the very end of Physics 1, if you had Physics 1 with me, we talked about how I was looking at, if I looked at my object and how it's going to compress due to pressure, this is a change in pressure over a change in volume divided by volume. And we saw that equation before, but this is really interesting here because this is a pressure. And one of the things that we know about sound is we can actually feel that pressure. And we talked a little bit about that on Friday as we were going through looking at our various waves and looking at how those things were happening. So if we were looking at, okay, what we're going to talk about intensity. So we said if we had an object like this and we actually moved it out, we noticed that as we moved further and further away, the intensity was going to decline. And we actually said that intensity was going to be declining. And actually, we can define intensity as my average power divided by the area. And as I was dealing with a spherical object, this is my power average, and I'm going to write it out because I don't want to get that confused with pressure. Even though our power and pressure when we're dealing with sound are related, they aren't the same thing. Okay? Remember that power is in watts, and we could go back and look at power as we dealt with that. This is my energy per unit time. So we talk about waves carry energy. And that's a fundamental thing that we have. So we're going to see this power divided by the area. And if I'm dealing with a sphere, we're going to look at the surface area of a sphere, and that's our 4 pi r squared. And that gets us to what we were talking about on Friday. So remember, Friday we kind of focused on things as dealing with conceptual items. Today we're kind of putting the mathematics with that together. But let's go back and let's look at intensity again. Okay, so intensity is, we are going to look at intensity as 1 over the area, and then that's my change in energy over my change in time. But remember, this right here is power. So my intensity becomes power divided by area. Now, the human ear is a very, very sensitive instrument. Our threshold of hearing, the intensity of sound for the human ear to hear, is equal to 1 times 10 to the minus 12 Weber meters. Meters should be meter squared. Yep, meter squared. That's the smallest intensity of sound that our ears can pick up. Now, our threshold of pain, because we know that the intensity of sound for the threshold of pain this is 1 Weber meter squared. Now, that's the human ear. And in fact, we're going to define our ranges of sound based on the human ear. So, ultrasonic, these are higher frequencies than we can hear. Sonic is the frequencies we can hear, and subsonic are below. And usually these are all dealt with frequencies. So intensity is kind of the volume. So intensity relates to the volume, frequencies relate to what we can hear. So we've got ultrasonic and subsonic and sonic. These are the ranges of sound that we can hear. Volume are the intensities, because I can have a frequency at a low intensity or I can have a frequency at a high intensity. So we start talking about quality of sound. And quality of sound relates to frequency, and that relates to pitch, if we're talking about musical instruments. Intensity relates to loudness. And then we have something that we call timbre, and that's going to be our color of our sound. So, and the best way to describe this is if I play a middle C on a piano, a violin, a flute, or a trombone, right? That middle C, even though it's the same frequency, whether it's played by the piano, the violin, the trombone, or the flute, even though it's played, that same frequency is there, and I can even have the same intensity, we hear something different. We hear that C on the piano as a different than if I'm making that middle C tone using a frequency generator on my computer. And that relates to the color or timbre of sound. So these are our sound descriptors. Okay, those are our sound descriptors. But coming back to our intensity, we're dealing with an intensity on the low end of 1 times 10 to the minus 12, and that's Weber meters squared. And our intensity at the high end of 1 Weber meters squared. This is 12 orders of magnitude. Okay, that's 12 orders of magnitude. And I'm going to see if ours doesn't necessarily have it. Our book doesn't necessarily have it. But if you go to the PowerPoint that I have in Blackboard so that you can actually look at it, we know that I have a scale here that goes from our low end, and these are in decibels. We're going to use a B here. And as we go up, our intensity increases. And a quiet room is down here. And a rock concert is up here. And our threshold for hearing damage is 90 decibels. And we also use this term for decibels over 8 hours. And if I'm in OSHA, the OSHA action level is at 85 decibels. Okay. So we have this huge range, and we have to use that huge range because we're looking at 12 orders of magnitude, and that makes it really, really difficult for us to work with those kinds of levels. So we came up with our decibel scale. And so that's why we use decibels, is because of that. So let's go in here. I'm going to get my phone out. And I'm going to come into my physics tools. And I'm going to go to my Firefox. And you can actually look at audio amplitude in sound. So I'm going to do this. So right now it's looking at our sound, and we actually translate pressure to deal with different things. So you can do that way. If you want to have something a little different, this sound meter app, this sound meter app is very, very close to an OSHA monitoring for, I don't want to worry about the update. Okay. So you can actually see the decibel levels in the room and monitor those decibel levels. So that's one of the ones when we do our 1 over R squared experiment, you can use either your Firefox app or one of these apps to be able to do that monitoring of the room. And our 56 is the background associated with the fans that are blowing in this room. So that gives you an idea of decibel sounds, and you can actually measure them yourself and work through things. So how do we do decibels? Well, our decibels are defined as 10 log our intensity divided by our threshold of hearing, and this is our I sub 0. Okay, this is our I sub 0, and that gives us our decibels. All right. So and I can also reverse. So if I have, let's say 85 decibels is equal to 10 log we know what I sub 0 is as 1 times 10 to the minus 12. So if I have 85, I get 8.5 is equal to the log of I over 1 times I to the 12. And now if I do my reverse log, I get 10 to the 8.5 is equal to I divided by 1 times 10 to the minus 12. So now I get 1 times 10 to the minus 12 times 10 to the 8.5. That's going to equal I. And remember, if I'm dealing with exponents here, I get 10 minus 12 plus 8.5, which is going to equal 10. So if I do my 12, I get negative 3.5. My intensity equals there we go. Minus 3.5. I end up with 0.0000316. And if I want to put this into WebAssign, this is 3.16 e to the 1, 2, 3, 4 minus 4. Okay. So you can work with that intensity. All right. And just as a reminder, because since we're going to do it as part of a lab, if I measure and I'm at 3 meters away and I measure my intensity, and I'm going to go ahead and measure my intensity because that's the way I can do it on my phone. So I'm going to measure my intensity at 95 decibels. And now I'm now 100. Now we're going to make it 30 meters away. And now my intensity is 50 decibels. Do I want to do it that way? No. I'm going to just do it this way because I may not be right. I want to know the intensity here. Okay. So if we know the intensity 1 is equal to the pressure average, 4 pi R1 squared, and intensity 2 is equal to pressure average, 4 pi R2 squared. I can solve for this and I get I1 over I2 is equal to, so if I do this, I get P average 4 pi R1 squared, 4 pi R2 squared, pressure average. Those cancel, and this becomes R2 squared over R1 squared. I1 over I2. I want to solve for I2, so I'm going to get I2 is equal to I1 R1 squared divided by R2 squared. So I've got to figure out intensity. I've got this in decibels. So we're going to do this again. I'm going to do my 95 is equal to 10 log I over I0, which now is 9.5 is equal to the log of I over I0. I get 10 to the 9.5, 10 to the minus 12 is equal to I, which is going to be 10 is minus 2.5. I'm going to go ahead and leave it like that because I can do that part. So I got 10 to the minus 2.5 times R1 squared, which is going to be 9 meters squared, and R2, and this is my total distance away now, is 30 meters squared. We can go back. So times 9 divided by 30 squared. I get an intensity, I'm going to go ahead and put it in scientific notation. I get an intensity of 3.16 times 10 to the minus 5. And if I want that in decibels, that's going to be 10 log 3.16 times 10 to the minus 5 divided by 10 to the minus 12. I'm going to take the log of that. And this ends up being 10 log, I'm going to write it down, 3.16 times 10 to the minus 7. Okay, I'm going to do log answer times 10 is going to give me 75 decibels. So if I were to take my measurement, go out and measure here at 95 and then measure here, I should see 75 decibels and be able to compare it with what we're doing. So again, you'll get to do this laboratory, but that's one way to do the problem. Okay. Questions so far? All right. So if I have a sound, and as we know, it's going to go out and it's going to travel, and I am now a person that's walking towards that sound, I'm going to encounter this wavefront. Now, the time between these wavefronts is the same. Okay, the time that's between these wave fronts is the same. But as I come to this, I'm going to come to the next. If I'm walking towards this, I'm going to hear the next wave sooner than if I was just standing still. And this gives us our idea of the Doppler effect. And we're all familiar with the Doppler effect. I mean, we stand on the corner and we hear the car coming. So if my car is coming and it's approaching, it's going to send out its sound wave, but it's moving the next one. So the next one is closer and I'm going to hear it coming towards me. But as I'm leaving, the next sound wave is further and further apart. So if I am standing at this spot, I see it a little differently. Now, in Blackboard, you have a couple of things. You have the slides, the PowerPoint slides that has a better diagram of this. You also have in there, you have some links to where you can actually hear the Doppler effect. But we get those Doppler effect items. So we actually look at the Doppler effect as two cases. We get case one, and case one is where the source, we've got, this one is case one. The source is fixed, but the observer is moving towards the source or moving away from the source, as the case may be. All right. And we're going to hear the frequency change. Remember that the speed of the wave is equal to the wavelength times the frequency. Now, what appears to change is the wavelength, because we don't get, when we talk about crest to crest and things like that, we actually get so for case one, the frequency of the observer is going to be the frequency of the source. And that's the velocity of sound. This is the speed of sound. Plus the speed of the observer divided by the speed of sound. So you're going to hear the frequency change. Okay. Now, as you work these problems in WebAssign, you've got to be very, very careful about your directions, right? Because if we are moving here, we're going to have a change in our frequency based on the direction. So you have to be very careful as to how this goes. Because if I am moving away, okay, so the speed of sound is going this way, and we say the speed of sound is 343 meters per second because we're in normal air temperature. And if my person is moving towards the speed of sound, let's say it's moving at 5 meters per second, we're going to get that change and my frequency is going to appear to decrease, or we're going to hear a decrease. If I'm moving away, we're going to see the other. Now, case two is now I'm the observer and I'm fixed, but the source is moving. Okay, case two is the source is moving. And so now it's going to look like this. So this is going to be my frequency of my source. And this time I'm going to get the speed of sound minus the observer in the bottom. And we're going to see a change based on that. Now, you can combine these two cases for the general equation. Our general equation. And that's going to be the frequency of the observed is going to be the frequency of sound And now I get the velocity plus the velocity of the observer, velocity minus the velocity of the observer. And this general equation works. Wait, this is the velocity. Hang on, I made a mistake. This isn't the observer, this is the source. Because the source is what's moving. Okay, that's the source. And this works for moving both the source and the observer. So this would be like the case where I'm headed down the road and the ambulance is coming towards me. Both of us are moving, so we're going to hear that Doppler effect change. So practice those Doppler effect problems because you got to keep track of the positives and negatives. All right, so we've got our Doppler effect in here as well. A couple things that we want to talk about is if we want to break the speed of sound and why breaking the speed of sound was such a feat. If I have a plane and it's moving, all right, and it's moving, and now it's moving at the speed where it's catching up with its own wavefronts, we end up with this cone effect, and ultimately we break through, where my vehicle is traveling faster than the source of sound that it is making. And that's when we break the sound barrier. And if I'm a person inside of my aircraft that goes through that, I don't hear a sonic boom. I don't hear it because I'm traveling at the same speed as the aircraft. So I'm not going to hear that sonic boom as we move through. And so you can actually see that cone. Our figure, there's a figure in the text. I've provided a lot of different figures where you actually can see that cone building as you build up on that pressure wave, remember, or that power wave as we get there and we ultimately break through. One of the things that we talked about last week are standing waves. And we talked about harmonics to get those standing waves. The things that you need to know about those is if I have a string, I'm going to have to be fixed at both ends, and that's a node. This is an antinode. And this would be one wavelength because I have a complete wave between my 2 points. But that's not my fundamental frequency. My fundamental frequency for a standing wave in this case would be a half a wavelength because I can get, this would be my first harmonic. And that's something that we talked about last week when we were dealing with our standing waves. And we talked about them in a pipe. So if I have a pipe, I have to have antinodes. If I have open-ended pipes, I have to have antinodes at both ends. And I have a node in the middle. And this, of course, is also half a wavelength. And if I have a pipe that has a fixed end, I can have a quarter of a wavelength. And then I can increase these as they move forward. All right. So we've got our air columns, our standing waves. There's a couple other things to kind of refer to. One is beats. And I will tell you, I don't do anything with beats. We talk about them. If you set up 2 frequency generators, say set one up at 350 and then set one up at 344, you're going to hear a wong, 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 wong sound. I don't actually hear them very well So I don't do a lot with them. That's when things are slightly out of phase. They're not quite in sync. You're going to get beats associated with those kinds of items. You'll get that wah, wah, wah sound. That goes back and relates back to this first part that we were talking about, our how we describe sound for ears and in our hearing. In Blackboard, you have a link to a really good simulation of how the human ear works. You know, we do have our eardrum, and then the three smallest bones in the body are right there, and that sends off a vibration that goes to our auditory nerves, which works with hair cells into the cochlea, and that's what the signal is that we pick up to hear. So that's one of the things that's in there. So what we've done so far is we've talked about waves. We've talked about the wave equation. We've dealt with sound frequencies, the Doppler effects, looking at intensity and all of those lovely things. Should have plenty of extra videos to kind of look through and catch up on. So you have those, and I'm going to stop here and ask questions. And if you don't have any questions, I'm going to turn you loose for the day. Just remember that you do have a test on Friday, and we will not have Zoom on Friday because of the test. I do give you that time for the test.